Hi, this is Somaiah working as assistant professor in the Department of Mechanical Engineering. Welcome back to the course of Fluid Mechanics and Hydraulic Machines. Today, in this session, I am going to discuss about the work done of a Kaplan turbine. So, previously we have gone through the Francis turbine and Pelton wheel turbine. So, based on its classifications, we are studying under reaction turbine. The reaction turbine, there will be a Francis turbine and a Kaplan turbine. So, but Pelton will be coming under impulse turbine. So, if you compare with the Francis turbine, Kaplan turbine is a axial flow reaction turbine. Francis is a mixed flow reaction turbine, but both are reaction turbines. These two will be utilizing the principle of reaction. So here the flow is axial, even though before getting into inlet of a turbine, there will be high pressure. After working on a turbine, there will be a low pressure. The difference between these two pressures is known as reaction. So due to in case of mixed flow turbine, there will be force extracted due to both kinds of energy. Similarly, here also there will be some energy will be remained in the form of kinetic energy, and substantial energy will be in the form of pressure energy. So the Kaplan turbine is invented by Professor Victor Kaplan, scientist of Austrian. So in 1913, so it was invented. So that's why it is named after Kaplan. So it was invented based on after modifications of different types of turbine. So because initially there was overshot wheel, undershot wheel, then the turbines based on impulse principle. There is a Pelton wheel turbine, Francis turbine. Before Francis, there was inward flow reaction turbine, outward flow reaction turbine, and a combination of inward flow plus axial flow reaction turbine. So this is purely axial flow reaction turbine. So this is invented after different type of after invention of different types of turbines. So if the water flows parallel to the axis of rotation of shaft, in this turbine, the axial flow means the flow direction of a water through the runner vanes is parallel to the axis of rotation of a shaft. So because as a shaft is located horizontally, the direction of water will be in the same direction. So as there will be vanes over here, the vanes will be here, the direction will be in the parallel to this one, but not tangential. If it is tangential, means there will be a pitch circle. In case of Pelton wheel turbine, the axis of jet will be tangent to the pitch circle. In that is tangent flow, but not axial flow. So this is axial flow, but not a tangential flow. The lower end of the shaft made larger, which is known as hub. The vanes are fixed on the hub, and hence the hub acts as a runner. Axial flow reaction turbine. For axial flow reaction turbine, hub acts as a runner. In case of Francis turbine, between the two plates, the runner vanes are arranged, and that is key to the shaft. So there will be there are two different axial flow reaction turbine. One is a propeller turbine, another one is Kaplan turbine. The Kaplan turbine blades can be varied. The angle between the blades can be changed, but in case of a propeller turbine, it's not possible. That is fixed. The angle between the runner vanes are fixed. When the vanes are fixed to the hub and they are not adjustable, then that is known as a propeller. But if the angle can be adjusted, means that is Kaplan turbine. But both are axial flow turbines only, and number of vanes also similar, but angle between the vanes can't be adjusted. So Francis turbine, here's Kaplan turbine, we can see as these two are comes under reaction turbines only. Both are reaction turbines. So in this slide, we can see the difference between Francis Kaplan turbine arrangements. So because this is axial flow reaction turbine, this is axial flow. We can see the water coming in this direction, and before entering into the turbine runner, so it became axial, because this is parallel to the rotation of a shaft. Rotation of a shaft is in this direction. The flow direction in the turbine also in the same direction. The both are parallel but not tangential or coincident. So they are they are axial. Therefore, this is known as pure axial flow turbine. Pure axial flow turbine. Here, outlet is axial, while coming out of the turbine is flow direction is axial. But before entering into the turbine vanes is radial. So in this case, radially they have to enter, and after working on a turbine, after rotating it, then it exits axially, parallel to the rotation of a shaft. The rotation of a shaft is like this. The vertical disposition of shaft. Here also vertical disposition of shaft. Both are vertical. So, but the vanes are the runner is arranged in such a way that the water has to enter radially inward, and after working on turbine, it comes out in axial direction. Therefore, it is nothing but mixed flow reaction turbine. Mixed flow, medium head, medium efficient turbine. So, and Kaplan turbine is high efficiency turbine. It is pure axial flow. Before and after working on the turbine also, the direction of water is completely parallel to the direction of rotation of a shaft. Therefore, is a pure axial flow turbine. So here the hub for a hub, the number of blades are adjusted, and these angle between these blades can be varied. So in case of a propeller, it is not possible. So therefore, the hub can be acted as a rotor. So in case of other turbines, see the blades are fixed in between the two plates. In between two plates, that will be acting as a rotor. So here also spiral casing is there, gradually decreasing cross-sectional area. As it is a reaction turbine, it must be submerged in a water always. So therefore, it will be surrounded by a scroll casing submerged in water. Now, after that, it enters into a stay vanes. After stay vanes, there will be guide vanes. The guide vane purpose is to adjust the angle of attack, and the amount of quantity can be supplied onto the turbine can be varied by using the guide vanes. So once the guide vanes are adjusted, it will be connected to the governing mechanism. The governing mechanism is based on the requirement. Governing mechanism purpose is to based on the demand of a power supply. It will be varying the angle between the guide vanes. It can be supplying more amount of water. It can be decreasing the amount of water by varying the angle between the guide vanes. So in this diagram, we can see the sectional front view and sectional top view of a Kaplan turbine. So before this, we have seen the arrangement of different turbines in a 3D. But here we can see only sectional view. Here it is a hub. There are 4 blades. This indicates 2 blades, and this is a hub over which there will be 4 number of blades. In general, the 4 to 6 blades will be fixed onto hub of a Kaplan turbine, and the water will be entering into a scroll casing, which is gradually cross-sectional area. Afterwards, it's to take a angle will be changed from this horizontal to vertical. So there will be 90 degrees conversion will be there. After that, so it will be entering onto the turbine runner horizontally and leaving also horizontally. So and there will be draft tube in order to increase the pressure, because after working on a turbine, the pressure will be decreased at the end of it. Before entering into the runner vanes, that pressure will be high, but after working on a turbine, the pressure becomes less, and kinetic energy, the velocity of liquid water will become more. But with that less energy, the less pressure energy, it can't mix with the tail raise level, tail raise water. So because the tail raise is at atmospheric pressure, in order to convey this water from outlet of turbine to tail raise, there is a requirement of draft tube. So here we can see there will be guide vanes, and before that stay vanes. After entering into the screw up from penstock. Penstock is connected between the reservoir, and from reservoir it carries the water and it submits to the inlet of a turbine. Inlet of turbine is begins from a the scroll casing. The scroll casing is gradually cross sectional area because in order to possess the two kinds of energy. So in case of impulse turbine, only one kind of energy is there, therefore less efficient one. But here there will be, in order to maintain these two types of energies, this is so shaped in such a way that it will have both kinds of energy before hitting the turbine runner. So here guide vanes will be there. After that the angle and the quantity of flow will be varied. Then it will be entering into the turbine runner. So the after turbine working on turbine runner, it causes to rotate, and as it is coupled to the generator shaft, it will be generating the power. So this is also we can see in this diagram the various components arrangement. This is also a sectional front view only. So draft tube and the diameter of a boss in order to calculate various problems based on the Kaplan turbine. This is a boss diameter, and say this is the outer diameter of boss, and dB is inner diameter of boss, and number of vanes, guide vanes, and arrangement of guide vanes, runner vanes. After that the how it is entering into draft tube, and how it is conveyed to the tail race. The Kaplan turbine is developed by Austrian engineer Victor Kaplan. It is suitable for low heads and requires a large quantity of water to develop large amount of power. So here, based on the available head on a turbine, less than 60 meters is a Kaplan turbine. So between 60 to 250 is a Francis turbine. But here it requires a large amount of water. This requires medium amount of water, and Pelton wheel turbine greater than 1800 meters, then it requires a less amount of water only. As the head is greater and it develops that required amount of energy to hit the turbine. So here, as it is less than 260 meter, it requires a large amount, and it develops large power also. This is high efficient turbine. So different components are scroll casing, guide vanes, hub, and fixed with a runner vanes, draft tube. The function of above components is same as that of a Francis turbine, as we have discussed in the previous class. The water from the penstock enters into a scroll casing, and from guide vanes the water runs through 90 degrees. So after that it changes its direction, then it becomes axial. So after that it enters into the runner vanes. The runner of a Kaplan turbine has 4 to 6 blades. In exceptional cases, maybe 8, but in general, in actual power plant installations, etc., 4 to 6. So majority of turbines of Kaplan turbines with 4 to 6 blades only. The blades attached to a hub also shaped in flow axially through the runner. The adjustment of the runner blades is usually carried out automatically by means of a servo motor operating inside the hollow coupling of a turbine and generator shaft. When both guide vane angle and runner blade angle may vary, high efficiency can be maintained. Even at pot load, when a lower discharge is flowing through the runner, high efficiency can be attained. This is the advantage of a Kaplan turbine, and it is a low head turbine. The runner blades are essential components in this turbine, which looks similar to a propeller turbine. But if you compare with a propeller turbine, the whose angle can't be changed. Angle between the blades can't be changed. The blade control mechanism controls the attack angle. The water hits the blade caused by the movable blade connection. It includes essential components of the Kaplan turbine. Simultaneously, the guide vane and runner vane angles are adjusted. The water under all the working conditions of flow through the runner blades without shock. As such, the eddy losses, which are inevitable in Francis turbine and propeller turbines, are almost completely eliminated in case of Kaplan turbine. So water takes 90 degrees twist in case of both Francis and Kaplan turbine. So when the water hits runner blades, then it starts rotating because of the reaction force of the water supply. These blades are twisted through their length to include optimum angle attack. So once the kinetic energy is changed into pressure energy, then water pressure can be increased. The turbine rotation can be used to turn. So because of the blade design, there will be two kinds of energies can be extracted from the water: the kinetic energy and also pressure energy. So the force, net force is equals to summation of these two. So in this video, we can see the working principle of a Kaplan turbine.
Kaplan turbines are suitable for power extraction when water energy is available at low head and high flow rate, which means they are suitable for operation when water is stored in a big reservoir at a relatively shallow altitude. In Kaplan turbine, flow is entered through a spiral casing. Decreasing area of casing makes sure that flow is entered to the central portion almost at uniform velocity throughout the
As the water is flowing from inlet to the exit of a pinched scroll casing, as it is decreasing cross-sectional area, less energy particles starts entering into a drop tube, entering into runner vanes.
Kaplan turbine is its runner. Cross-section of runner blade will have a curved shape. When water flows over it, it will induce a lift force due to airfoil effect. Tangential component of lift force will make the runner rotate. This rotation is transferred to a generator for electricity production. Kaplan turbines are axial flow machines where absolute velocity of flow is parallel to axis of turbine. Water is precisely made to pass through runner blades with help of a shroud. Power demand may fluctuate over time. A governing mechanism, which controls position of guide vanes, is used to control water flow rate. This can meet for varying power demand. Blades of Kaplan turbine are designed to operate under a wide range of operating conditions. A rotating blade experiences relative velocity of flow. The fundamental thing in blade design is relative velocity of fluid flow should be at optimal angle of attack at all cross sections.
And some relationships to calculate various parameters of a Kaplan turbine. We should go through different relations. The relations are for first relationship is expression for Q, that is 5/4 outer diameter of a runner, and dB is diameter of upper inner diameter, d0 square minus dB square into VF1. This is a flow at inlet, velocity of flow at inlet. So another relationship is blade velocity is 5 d naught n by 60. 5 d naught n. This is outer diameter. So u1 equals to u2. Here both are with the same velocity. u1 equals to u2 equals to 5 d naught n by 60. So and another relationship is the velocity of flow at inlet and outlet are equal. So therefore VF1 equals to VF2. And we can see the next relationship is the area of flow at inlet is equals to area of flow at outlet. That is equals to 5/4 d0 square minus dB square. Both flows are equal. And in case of Francis turbine, we have seen the U1 is equals to 5d1 n by 60, U2 equals to 5d2 n by 60, U1 is 5d1 n by 60, but here U1 equals to U2. So the relations are different from Francis to Kaplan. The expressions for work done will be same as that of Francis turbine. The work done we have seen rho A V1, rho A V1. The work done is rho A V1 into VW1 plus U plus or minus VW2 into U. Here as U equals to U1 equals to U2. Both are same. Therefore into U only. Here we can see in actual installations the Kaplan turbine view is we can see how many number of vanes will be there, how it will be installed in actual locations. In generally 4 to 6 only. In exceptional cases 8 vanes are like this, and it is going to be mounted, and its shaft is connected to a generator shaft, and it will be connected to a scroll casing. The scroll casing is connected to a penstock which carries water from a reservoir. Then gradually the water is as it is gradually decreasing, the water it will have both kinds of energy, and it enters after taking a twist of 90 degrees. It enters axially over a turbine vents and leaves in the axial direction only. After that it enters into a penstock with the help of a draft tube. So this is the actual image of a Kaplan turbine rotor. We'll see one example. The hub diameter of a Kaplan turbine working under 12 meter. So the diameter of hub is 0.35 times the diameter of runner. So there will be DO and DB. So the turbine is running at 100 RPM. The outlet outlet angle is 15 degrees. Outlet vane angle is 15 degrees. And flow ratio, psi is given 0.6. So you have to determine runner diameter, boss diameter, discharge is Q. Velocity of while at outlet is 0. So when beta becomes 90 degrees, while velocity is 0. So yeah, flow ratio is given as 0.6, and another relationship is boss diameter is equals to 0.35 times of the outer diameter. So n is 100 and psi is 0.6. From this we can calculate VF1. VF1 equals to psi into root 2gh. Therefore 9.2 meter per second. VW2 is 0. So therefore, beta is 90 degrees. So from the tan phi outlet velocity triangle, we can see tan phi equals to VF2 by U2. VF2 by U2. Therefore, this is equals to VF1 by U2, and as phi angle is given, outlet vane angle is given as 15 degrees. Therefore, we can calculate U2 as we have determined VF1 equals to VF2 equals to 0.6 into root 2gh. Therefore, we have VF2 also. VF2 is there and angle phi is there. Therefore, from this you can calculate the blade velocity U2 34.33. So U2 and U1 both are same. U1 equals to U2 in case of Kaplan turbine. So from this we can calculate outer diameter D0. So D0 equals to 6.55 meter. Therefore dB is 0.35 times of D0. Therefore 2.3 meters. So Q is given as 5 by 4 D0 square minus dB square into VF1. Therefore D0 is known, DF is known. Therefore Q equals to 271 into 77 meter cube per seconds. Q is 271 meter cube second. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.